My name's Ron Leonard. I'm going to expand a little bit more on the FANUC robot frames. Our objectives are to discuss the Cartesian coordinate system, what is a coordinate system, and then what are the coordinate systems that the FANUC robot uses. There's world, there's joint, there's tool, there's user, and there's jog. So a Cartesian coordinate system is a way of finding something in space. We need to be able to tell the robot where to go in space. So a Cartesian coordinate system is two perpendicular axes labeled x and y in this example, where x and y denote how far that point is in those directions. So I can find that point in space by, for example, 600 or 800 millimeters, x, y. So if we go in 3 dimensions, we add the z-axis. So x, y, and z, 3 different coordinates will find a point in space. In robotics, with the FANUC robots, typically z is up and down, x is forward and back, y is right to left. So if we look at the teach pendant on our LR-Mate 200 IC, there are buttons that we can press to move the robot, and a button called COORD, coordinate. And this is, will cycle through our choices. If I cycle through, I see world, I hit the button again, I see tool, I see user, I see joint, I see jog frame, and then back to world. It cycles through. So this is telling the robot which coordinate system I want it to use as I tell it, give it directions to move in space. So the first one is joint, and this one is a little bit more different than all the others. The joint coordinate system doesn't rely on the Cartesian x, y, z. And in fact, it is more very directly related to the physical makeup of the robot itself. The FANUC robot is 6 axes. Basically, it can rotate at the base, at the shoulder, at the arm, the wrist, the arm, and the faceplate. So there's 6 servos that can rotate counterclockwise or clockwise, and by moving those 6 axes, I can affect not only a location for the end of my robot, but also the orientation. Do I want to be approaching from above? Do I want to approach from below? I want to approach from the left or the right. So the joint coordinate system is the best way to get the proper orientation of what you want. It's also, if you're in a situation where you're trying to get out of a tight squeeze, sometimes joint is better than other coordinates because you know it's this axis that you want to move. So you'll move exactly and only that axis. So when you use the teach pendant, there's J1, J2, J3, J4, J5, J6, and then clockwise and counterclockwise for each of those joints. So these 12 buttons are what's going to control the rotation about each of those axes, and so you know what to expect. Before you press the button, you know what's going to happen. And that's important. If you're in tight quarters, you better know what the robot's going to do when you press a certain button before it does it, or you'll get surprised, and surprises are never good. So the rest of the coordinate systems are all the x, y, z Cartesian coordinate systems. So let's start with the world. If we look at the robot, if I'm behind the robot, the base of the robot is my origin of my x, y, z axis. And if I use my right hand, I can simulate 3 perpendicular axes, z, x, and y. And I can visualize those 3 axes at the center of that robot. That's the robot's world. So now when I do something with the robot and I move in a particular direction, I know what it's going to be. It's going to be, z is going to be up, x is going to be out, y is going to be over. So it's more intuitive, and you'll make less mistakes if you're in the world coordinate system. This is probably the coordinate system you'll use the most often. So those same 6 keys now take on a different meaning. Now instead of J1 through J6, they're X, Y, and Z. So you can hold the shift key and hit Z plus, and the tool end point, end of arm tooling on the robot will go up. You can hit the POS key on the teach pendant and get the position, and you can toggle between this screen, which is the world position screen, X, Y, Z, or you can toggle it into joint and it'll tell you the actual encoder values of the 6 axes. Those are kind of hard to reconcile. They don't really tell your mind what's going on so much, other than directionally you can see them moving. So a tool frame is the same XYZ coordinate, but we're going to move it. We're going to move it either out to the faceplate of the robot, which is the default, or if we have a certain kind of tool, like a weld gun or a paint gun or spot welder, grippers, we can move our tool center point all the way out to the business end of our end of arm tooling. So it's still XYZ, but now think about what happens. Now my origin and my axes are oriented to the tool, not to the base of the robot. So when I move the tool, the origin of the world coordinates doesn't move. It's still at the base of the robot. But the origin of the tool coordinates, the tool frame, is going to move along with the tool. So that allows you in your programming to be a little bit more flexible, a little bit more intuitive of what the tool is doing as you program it. So the tool center point all depends on the tool. In paint, it's 12 inches from the applicator. That's the business end of the paint gun. Arc tool, the business end of the arc welder. And spot tool, where the gun tips meet, business end of the spot welder. Handling tool, where the gripper closes. Again, the business end of the gripper. So user frame, as opposed to tool frame, the tool frame, remember, moves with the tool. The user frame is not going to move. The user frame is another XYZ coordinate system, but now the origin and orientation of that X, Y, and Z is with the workpiece. Maybe I'm working on a fixture. Maybe I have 2 or 3. What's nice about the user frame, but can get you in trouble, is if you teach in that user frame, it's all the points that you teach are relative to the XYZ origin of the user frame. So if you ever move everything, you move it over 2 inches and you rotate it 45 degrees, you can take that user frame, move it over 2 inches, rotate it 45 degrees, and now you don't have to change any of your points in your program, because your whole program moved because it was all relative to that user frame. That's the good news. The bad news is if you don't know what you're doing or somebody else did it, it could be confusing. All right, now jog frame is just like user frame. I create an XYZ somewhere that's different than the world frame, but now I'm just jogging to those axes. I'm not actually saving points relative to that axis. So it's only for jogging, hence the term, it's a jog frame. It's a jog-only frame. It doesn't actually affect those saved points. So in conclusion, we talked about Cartesian, X, Y, and Z. We talked about 5 different coordinate frames: joint, world, tool, user, and jog. Thank you. Any questions?